Hi, this is lecture 19 of MA 221, and today we'll be discussing about alternating series. Okay, so first let us look into the definition of the alternating series. So an alternating series is a series of alternative terms. Is a series where the terms alternate in sign. Okay, for example, like a1 minus a2 plus a3 minus a4 plus a5 minus a6 and so on, like this, or minus a1 plus a2 minus a3 plus a4 minus so on. Okay, like that. For example, one pretty famous example is minus 1 to the n minus 1 over n, which is 1 minus half plus 1 over 3 minus 1 over 4 plus 1 over 5 and so on. Okay, this is basically the harmonic series, but in harmonic series you have all the positive terms, but in this series you have positive and negative terms coming into the picture alternatively. Okay, now the main goal of this lecture is to deal with alternative series. So far all the tests and all the results that we have seen mainly deals with series as having only positive terms. But what if the series alternate the sign? Um, then how to deal with those series as? So if the terms of an alternating series are decreasing in magnitude and tend to 0, then the series converges. Okay, so in other words, if I have the series like this, a1 minus a2 plus a3 minus a4 and so on, or minus a1 plus a2 minus a3 plus a4 and so on, with ai bigger or equal to 0, okay, and an plus 1 is less than an for all n. So I'm not considering the sign of the terms, I'm just taking the magnitude. And if the magnitude is like decreasing and limit of an goes to 0 as in tends to infinity, then the series converges. Okay, this is in terms of notation. One small note here, if limit an is not equal to 0, then the series diverges. Do you recognize this? This is basically divergence theorem. So this result in alternative series tells you that if limit of an goes to 0 and the terms are like decreasing, then we have the convergence of the series. Okay, cool. Examples. So here we'll talk about this 3 example. The first example is, in the first example, I have an to be 1 over square root of n plus 2, right? So in all of these three, the -1 to the n says they are all alternating. Okay, right? So therefore, we can use the alternative series test. So here in the first example, my an is 1 over square root 2 plus square root n plus 2. Okay, so you can easily check that an is decreasing. Okay, and the reason is like when n increases, square root of n plus 2 also increases. So 1 over square root of n plus 2 decreases. And that is basically decreasing terms, right? When n increases, fn, decreases. So therefore the series actually is decreasing. Okay, I hope things are making a little bit sense. And also limit of an tends to infinity. In this case, limit n tends to infinity, 1 over square root of n plus 2 is basically 0. Okay, so therefore by alternative series test, this is an abbreviation of alternative series test, I can say that summation -1 to the n square root of n plus 2 converges. Okay, for the second example, I have an to be ln n over n. So the other way to check the decreasing terms is we can consider fn to be ln n over n, and then f prime n it will be minus ln n minus 1 over n square. You can check that. It's like basically probably product rule. This is less than 0, okay, for n to be bigger or equal to 5. So therefore this is decreasing. This is the first derivative test for increasing or decreasing functions. You may have encountered this in Calc 1. Okay, so therefore the series is decreasing. That's fine. So therefore we are on track. The next thing you need to check is limit n tends to infinity an, which is limit n tends to infinity ln n over n. So this is like a perfect condition to apply L'Hopital. So it'll be 1 over n over 1 limit n tends to infinity by L'Hopital, which is 0, right? So therefore, again by alternative series test says summation ln minus 1 to the n minus 1 to the n ln n over n converges. Sweet. Okay, I have one more example. So for that, I need to take one more page, I guess. Okay. For the third example, I will have an to be 2n plus 1 over 5n, right? Yeah. And so here, what we can do directly is you can first see. So it'll be a good idea in every example where you need to apply alternative series test is to evaluate the limit n tends to infinity an first. Because in this example, I can see that this will be not going to 0, I guess. Okay. So this is just 2 over 5, which is non-zero. So by, divergence series test, summation minus 1 to the n, 2n plus 1 over 5 diverges. Yeah, cool. The next topic is to estimate an alternative sum. Okay, what is that? So basically the thing is that when you have the alternative series test to be converging, then you need to basically ask yourself that how close I am from the limit. Okay, so if I put that in mathematical terms, so in most of the cases when you have a alternative series converging, say to S, then what happens is that your S1, the n partial sum sequence of the series given typically moves like this. So S1 will be there, S2 will be there, S3 will be there, S4 will be there, and like that way they will try to converge towards S. Okay, so let S be summation n equal to 1 to infinity minus 1 to the n a n, that is be a convergent um, alternating series, then S lies between any two consecutive partial sums, right? So S1 is the first one and then S2 is the second one, or the two consecutive partials and partial sums. Then you can see that S is always in between S1 and S2. Similarly, if you take, say, S3 and S4, then again S is in between S3 and S4. That's what the sentence is trying to convey. Okay, then, and more so, Rn is S minus Sn. So say Rn is the error when you take the n partial sum. So for example, say R5 will denote S minus S5. When you consider the first 5 terms of the series and you try to see that what is the error in the fifth partial sum and the limit, that is basically R5. The remainder are error. That is approximately sorry. That is approaching S by the nth partial sum satisfying Rn modulus of that is less or equal to an plus 1. So basically this is the formula that we need later. Okay. So if I look into one example, say the question is asking you to estimate summation minus 1 to the n over n factorial so that the error is less than 0.001. So basically what they're asking is, can you find the n for which the n partial sum will be, 0.001 far from the actual limit. So say this is converging to say S. So this is converging to S. Then the question is asking, can you find what is N for that this will be bounded in between, say, Sn and Sn plus 1, like this. Okay. Okay, so to solve this, we know that so we know that this formula holds. So an plus 1, which is just 1 over n plus 1 factorial, right? Because this is nothing but minus 1 to the n an summation, right? So an will be like without the minus 1 to the n. And that is by the formula that is bigger or equal to 0.01. Okay. No, I'm wrong. Sorry. Okay. So an is of course 1 over n plus 1 factorial. And I know that Rn is basically less or equal to this, right? And I want my error to be smaller than 0.01. So if I take an plus 1 to be smaller than 0.01, then obviously my Rn will also be smaller than 0.01. So this is the right inequality. But from this, what I had to do is I have to solve for n. So I have 1 over n plus 1 factorial is equal to 0.01. I have taken bigger than equal to in the when I was solving it first, which is wrong. Okay. So then this will be n plus 1 factorial is bigger or equal to 1 over 0.01 by cross multiplying, which is nothing but n plus 1 factorial is bigger or equal to 100, I guess. Yes. And now for what n this inequality holds, that's the question. So we have to put n equal to 1. So obviously for n equal to 1, this is 2 factorial, which is not bigger or equal to 100. And then we increase the n. So I can say that 4 factorial will be 24 and 5 factorial will be 120. You can check it, which is bigger than 100. So if I take my n to be 4, then n plus 1 will be 5 factorial, which is 120, which is bigger or equal to 100. So n equal to 4 will do my task. So therefore, what I can say is, minus, so this is the sum. This will be in between minus 1 plus 1 over 2 factorial minus 1 over 3 factorial plus 1 over 4 factorial, right? And then minus 1 plus 1 over 2 factorial minus 1 over 3 factorial plus 1 over 4 factorial, space, minus 1 over 5 factorial. So the sum will be bounded in between this two number. Okay, this is Of course, you can see that this is bigger than that, right? Because here you have negative 1 over 5 factorial. So this is lesser than that. So that's why this quantity will be in the left-hand side. Okay. So in the homework, you will find some of the problems where you basically need to find what is your n. Okay, cool. The next topic is to find um, um, so the next topic is to find which series are like more nicer than the alternative series. Okay, so let me introduce the definition of absolute convergence. So a series summation an called absolute convergent if summation over modulus an converges. So if the absolute term series, if I consider, so given a series, if I consider only the, magnitude or the absolute values of the terms and construct a new new series out of it, and the new series converges, then we call the original series an to be absolutely convergent. Okay. On the contrary, if summation an converges, but when I take the absolute value, then that series diverges, then summation an is called conditionally convergent. Let me give you one example to like make things a little bit simpler. For example, we have dealt with summation 1 over n. This is harmonic series, and this is divergent, right? Okay. But summation minus 1 to the n, 1 over n, this is convergent, right? Maybe a little bit more space. Okay, so if this was my original series given, then the original series is actually convergent. But when I take the magnitude only, then that series is diverging. So therefore, what we can say is summation minus 1 to the n, 1 over n is a conditionally convergent series. Okay. On contrary, if we take minus 1 to the n, 1 over n square, then the magnitude of the terms will be just 1 over n square. I know that by P series test, this is convergent. And if you use probably alternative series test, then you'll get, then you'll get this series to be convergent as well. Right? So therefore, no matter if I take the magnitude only or the alternative series, both of those are convergent in this case. So therefore, my original series, which was minus 1 to the n, 1 over n square, is absolutely convergent. Okay. I hope things are a little bit making more sense. Okay. There is a theorem in this context that I state without the proof, which is if modulus of an, that series is convergent, then summation an also converges. Okay. Okay, so one example to illustrate the theorem is summation n equal to 1 to infinity sine 7n over n to the third. Is this convergent or not? So if you try to use the test that we have discussed so far, probably you will uh, get to know, but one of the easiest way is to use the theorem. So if I consider the modulus of an in this case, say this is just summation an, then that will be sine 7n modulus of that over into the third. And I know that sine, the function, the trigonometric function sine is bounded by 1. So in fact, bounded by 1 and minus 1 from the above and below. So in this case, I can write this inequality like this. And this is convergent by p-test, right? So this is a nice example actually. So by comparison test, I can use comparison test with this and that. This is convergent. So by comparison test, and obviously when I consider summation modulus of an, this is a positive term series. So I can use alternative series test. Sorry. I can use the comparison test, right? So by comparison test, at the right hand side, the series is converging. So therefore, that modulus of an series will converge as well. And by theorem, summation over an, which is summation n equal to 1 to infinity, sine 7n over n to the third, will also converge. Okay. The last few examples in this, I'll basically try to discuss which series are absolutely converging, which are conditionally converging, and which are diverging. Okay, cool. Okay, so for example A, so if I take modulus of an, then that will be just 1 over this. So this is the summation an, okay, n equal to 1 to infinity. And if I take my bn to be 1 over cube root of n square, okay, which is just 1 over n to the 2/3. And then if I use limit comparison test, limit of modulus of an over pn and tends to infinity will be it will be limit n tends to infinity 1 over n square plus 1 over or n square, okay, which is limit n tends to infinity cube root of n square over cube root of n square plus 1, and then basically I can use the trick here to write this as 1 plus 1 over n square like this. And this is 1, which is, so by the first result of limit comparison test, I can say that summation modulus of an and summation bn converges or diverges together. Right? But if I look at summation bn, which is summation 1 over n to the 2/3, this diverges, right? By p test, where p is 2/3, which is less or equal to 1. Okay. So summation modulus of an diverges. Okay. As the modulus series is diverging, so what I can say immediately is -1 to the n to the series. Okay. Cube root of n squared plus 1 is not absolutely converging. Okay, but it might be conditionally convergent, right? Okay, so for this series, the best thing should be to try the alternating series test first. Okay, so again, you can see clearly that this is decreasing because there is n square in the bottom, square root of cube root of n square actually. So it will be decreasing. And then for the second part of it, this is obviously going to 0, right? So it converges. Another I just mentioned the series actually. -1 to the n cube root of n square plus 1 n equal to 1 to infinity converges by alternating series test. Okay, cool. So therefore I can say that summation n equal to 1 to infinity -1 to the n cube root of n squared plus 1 is conditionally convergent. Okay, because though this series as it is converging, the modulus, if I take the modulus of the terms, then that series is diverging. That's why it is conditionally convergent basically. For the second example, for B, so if I take modulus of an in that case, so rather I just name it again, say consider this to be summation over an n equal to 1 to infinity. Then modulus of an will be basically 1 over square root of n to the 3 plus 1. And then if I take bn to be 1 over square root of n to the third, then this is nothing but 1 over n to the 3 over 2. And then limit of modulus of an over bn. If I consider it, so basically I'm doing the same process as like the problem A. Then this will be limit n tends to infinity 1 over 1 or third, which is mid. And tends to infinity. Square root of n to the third plus square root of n to the plus 1. But again, this is just limit n tends to infinity, 1 over 1 plus 1 over n to the third. Okay. And this is 1. So summation of so by limit comparison test, summation modulus an and summation bn converges or diverges together. But in this case, summation, okay, again, summation bn, which is summation n equal to 1 to infinity 1 over n to the 3 over 2 converges, right? As by p test 3 over 2, p equal to 3 over 2, which is bigger than 1, okay? So summation over modulus an, in other words, which is n equal to 1 to infinity, 1 over square root of n to the third plus 1 converges, okay? And obviously by the theorem that I mentioned just a few minutes ago, and by theorem, summation over an, which is summation n equal to 1 to infinity minus 1 to the n over n to the 3 plus 1 converges as well. Therefore, summation minus 1 to the n over square root n to the third plus 1 is absolute convergent. Okay, sweet. For the third example, is that okay? For this example, what I have is again modulus of an. If I consider that, then that is modulus sine n over 3 to the n, right? So say this is summation n of 1 to infinity. Okay, but then this is again less than 1 over 3 to the n, which is just 1 over 3 to the n. Why this inequality holds, I have already discussed in one of the examples. Okay, because modulus of sine is bounded by 1. Okay. Now this is basically geometric series with the common ratio to be 1/3, okay, which is less than 1. So therefore this is convergent. So obviously summation third to the n converges, and hence by direct comparison test, you can check that why I can apply the direct comparison test here. That is like a homework for you. Then by that summation over an converges. That is summation n equal to 1 to infinity modulus of sine n over n 3 to the n converges. And this implies by theorem summation n equal to 1 to infinity sine n over 3 to the n also converges. So sine n over 3 to the n summation n equal to 1 to infinity is again absolute convergence. And this is it for today's lecture. Try to see and solve the homeworks, like homework problems. And if you have any questions, you can mail me or meet me in the office hours. Okay, thank you.